Hi, and welcome back to the second session of the ViViMaT workshop. The last talk of today will be held by Chiara Gattinoni, who is a research fellow at ETH Zürich, where until recently she also held an individual Marie Skłodowska-Curie Fellowship. She is also an academic visitor in the Tribology group of Imperial College London, and the co-organizer of the West Seminar Series on Tribology, where I had the honor of giving a presentation recently. Her research interest is computational surface science in the areas of lubricant formulation and catalysis. With her talk, we move away from contact mechanics and head first into modeling the chemistry of additives. Chiara, the audience is all yours.
Hi, everyone. Thank you very much for taking the time to watch my talk. And thank you very much to Stefan and Karsten for inviting me to talk at ViViMaT. I would like to spend the next 15 minutes or so talking about the secret life of lubricant additives, or in more simple words, the atomistic behavior of lubricant additives studied with ab initio computational methods and with spectroscopic experiments. So we all know that lubricants have a zoo of additives added to them, which have different functionalities and behave in different ways. And in general, what we know about these additives comes from macroscopic experiments. So we know their macroscopic behavior. So for example, for an antifoam agent, we will know how much foam will be formed with stirring, for example, with or without the additive or with different additives. For a corrosion inhibitor, we have a picture here, we will know how much tarnishing occurs when we add the additive or not. For a friction modifier, we will know the effect on friction of different types of additives. And again, for a viscosity modifier, we will know the effect on viscosity of adding different types of additives to the mixture. So we will have information about the macroscopic behavior, but we will have very little to no information on the atomistic behavior, the nanoscale behavior. So there is, in general, quite a big gap to bridge between what occurs at the nanoscale and how it affects the macroscopic behavior. And I think it's an important gap to bridge, because if we know the behavior at the nanoscale, if we know the atomistic behavior, then it helps us understand the mechanism which results in the macroscale behavior. And it helps us to think of how we can change the mechanism to improve the behavior, to make it more efficient. So I will try to convince you that this is actually important, and it can be done using one test case because of time restrictions. And the test case that I want to talk to you about is the corrosion inhibition of copper. I think it's an important topic. Not only because it's historically important, it's been studied for a long time because there's lots of copper in piping and roofing and historical artifacts, but also because with electric vehicles, which contain a lot of copper, this problem is becoming more and more relevant. So let's spend 1 minute looking at how corrosion and oxidation and corrosion occur. So if we look at here, there is an idealized metal surface. It will interact with an environment, let's say a liquid, and in the liquid there will be things, molecules which interact with the surface. I put here some oxygen, water, sulfur-containing molecules. And what will occur is that they will interact with the surface, they will dissociate, and then maybe the oxygen will diffuse through, or if it's, let's say, a sulfur-rich environment, the sulfur will diffuse through. And we will form, for example, an oxide structure if it is the oxygen. And there's these two ways in which this can cause damage. The first way is by leaching out of the atoms in, let's say, the liquid, or if the lattice content of the oxide and the metal is different enough, then there will be flaking off of this oxide layer. So what we want to go is go from this picture where there is this oxidation and corrosion occurring to a picture where there is very little of it happening. And this can be done by adding a corrosion inhibitor. So corrosion inhibitor, I'll show you one here, and it's the one inhibitor I will talk about in my talk. It's called benzotriazole. It's an organic molecule which has a polar head, which is this triazole ring, and this carbon ring. And it will interact with the surface in some way. And in some way, which again, this molecule has been studied for over 50 years, but we still don't really know about how it works. In some way, it will stop this whole process occurring. So whether it is just a physical barrier, which is very strongly adsorbed to the surface and doesn't allow space for other molecules to approach the surface, or whether it changes the electrochemical behavior of the surface, and so the molecule cannot dissociate anymore, for example, we don't really know. So how do we go about studying this system using ab initio computational methods? So first we consider two flavors of this molecule, the intact molecule and the deprotonated one. And then what I did, I took a slab of copper 111, which is the facet of copper, which is the most stable. So it should be the most present even in polycrystalline copper. And then I added these molecules on the surface in different arrangements, optimized the system and extracted the energies. And these three systems that I show you here, one flat hydrogen bonded and two upright systems have more or less comparable energy. So they could all occur at room temperature. For the deprotonated system, there's 4 candidates. In this case, hydrogen bonding is not possible, and so the molecules are connected by these copper addatoms, which I show here in gray. So we now have 7 candidates. And how do we find out which one occurs in the real system? The short answer is that, well, we can't really by ourselves. So we need help from experiments. And I think this is really the first hint that this system is a pretty complex system. So if we think about it, there's many degrees of freedom. It can be protonated, it can be deprotonated, it can absorb through the azole moiety, or it can absorb via this van der Waals interaction with the benzene ring. Its behavior depends a lot on how many of these copper atoms are available on the surface. So it is a system which is not trivial at all. And another hint that this system is not trivial at all is by taking a little trip into the literature and looking at the catalog of structures which have been postulated for benzotriazole on copper 111. I'll show you here 3 of them. For example, in this case, it's flat-lying, connected with copper adatom. This is upright, hydrogen bonded. These cases like cute little flowers of dimers. And so there's different spectroscopic methods have been applied. So in this case is scanning tunneling microscopy. Here it was X-ray photoelectron spectroscopy. And really with these methods, first of all, it's very hard, if not impossible, to see the addatoms. It's very difficult to determine what is the precise structure and cleanness of the surface, how many of these addatoms, for example, are available. And it's really hard to go from a spectroscopic signal to the supramolecular geometry for such a complex molecular structure. So what we thought, this is a good moment to join forces. So from our point of view, experimental data can help us go hopefully from 7 to 1 candidate structures. And from an experimental point of view, our calculations could help interpret the experimental data. So if we take our 7 candidate structures and we calculate using ab initio methods the NEXAFs and the XPS theoretical spectra, we find this. Now, if you don't know what exactly NEXAFs and XPS experiments are, it's not so important. The gist of it is that X-rays are shown onto the surface, onto the system, and the system responds with a specific signal by varying the photon energy, and one can create these spectra. What is important is that each one of these systems has a very specific signature. You can really see how different they are from one another. So this gives us good hope that we can compare these signals to the experimental signal and be able to tell what we're looking at. We'll be able to go from 7 to 1 candidate structure. So this is what we did. We started with the X-ray photoelectron spectroscopy. So in black here are the experimental data for the low and high coverage. They look pretty similar. There is one main peak with a little shoulder about 1 electron volt apart. Up here are the data for the fully protonated molecule. And down here, the data for the protonated molecule. So the first thing that we can tell is that at room temperature, the molecule is deprotonated. So here, this spectrum has got 2 peaks, 2 electron volts apart, whereas these two have got 1 main peak with 2 secondary peaks. So none of these 3 correspond to the data in the black line. When we look instead at the protonated one, more or less all 3 could be. So this is as much as the XPS tells us. The benzotriazole will be deprotonated at room temperature. This is already helpful. We go from 7 to 4 candidate structures. So now we look at the NEXAFs. So the way the NEXAFs work, you see there's all these angles here. Each line corresponds to an angle. So the X-ray is shown onto the system at a specific angle, and by varying the angle, we get different spectra. And this gives us information basically on the tilting of the molecule. Now, again, what we did, we compared the spectra. So these are for probing the nitrogen, and these are the spectra for probing the carbon. These are the theoretical ones, and these are the experimental ones. And you can see that for the nitrogen, maybe the monomer could go, also the low coverage chains, more or less all of them could go, not super precisely, but yes, they're all okay. However, for the carbon, you see that the highest intensity is obtained for this 67 degrees, which we never see in our theoretical results. So we got really confused. How could it be? How could this occur? And we started thinking that maybe there could be a mixing of structures that have different signal that could give sort of this inversion between the 87 and the 67. But we had to bring in a third experimental technique to help us. And again, I'm not going to exactly explain what it is. It's called normal incident X-ray standing wave, and it measures the molecule surface distance. So we could compare the molecule surface distance measured with this experimental technique and the molecule surface distance that we measured in our calculations. And the only way for the data to fit together was to have 70% of dimers, so this structure here, and the minority 30% of low coverage chains. And indeed, when we plot the theoretical spectra with the weights as found through this third experiment, we found an extremely good agreement for the nitrogen K edge and the decent, good enough agreement for the carbon K edge. And considering how much noise there is in the carbon K edge data, which is normal for this kind of experiment, this is good enough. So by using 3 different experimental techniques and computational quantum mechanics-based methods, we were able to finally disentangle what is the structure which was for so long elusive of benzotriazole on copper 111. And now the question, and here you can find the relevant papers. Now the question is, okay, now we found the structure, which is great. Does this tell us anything about the behavior of benzotriazole? And I think the answer is yes. So this is still work in progress, but we can already see some interesting results. So if we take this dimer structure, which is the dominant structure on copper 111, and we add oxygen, and then again extract the energies, we find that the structures, the adsorption structure of oxygens which are favorable are those basically which are far away both from the copper adatom and the benzotriazole molecules. So the atom will not want to stay in the bulk or in any proximity of the dimer itself. And again, this might seem obvious, but it is not. It was really not known before what happens to the molecules and to the oxygen once the molecules are absorbed. And so this maybe starts giving us some ideas on how can we make benzotriazole better. So we could, for example, try and increase the coverage, increase how the molecules cover the surface. And this could be, for example, engineering molecular structures which promote flatline molecules. That could be by, for example, engineering the surface for having more addatoms or higher adatom mobility to favor chains which are lying more flat and then cover more of the surface, or force supramolecular structures of BTAs by creating, for example, molecules with a polymeric backbone, which again lie flat on the surface. This is, as I said, is still work in progress, and we'll see what we'll be able to do with it. But already having the structure of benzotriazole on copper 111 was a big breakthrough. So I hope that in these 15 minutes, I've convinced you that ab initio computational methods are actually a powerful tool to understand systems that we generally only think of on the macroscopic level. For benzotriazole, we found that the surface structure is mostly dimers, and the knowledge of the surface structure allows us to then start thinking what happens when the surface is covered by this dimer, but there's also oxygen or other oxidizing or corroding agents coming onto the surface, and it helps us thinking on how we can then make benzotriazole better. So this work was done with Angus Michaelidis, which is now University of Cambridge, and the experimental work was done by Gero Held and his group at the University of Reading and at Diamond, and the calculations were done on Archer. So I would like to acknowledge and thank all of them, and I would really like to thank you all for listening to my talk.
Thanks for a cool presentation, Chiara. I always have to do a tip of the hat to people who actually understand ab initio calculations and can produce useful results with them. Please leave your questions in the comment section below the video so Chiara can answer them in the live session on the 3rd of December. I wish everyone a good evening, and I'll see you at the third and last session of ViViMaT in a couple of days. If you subscribe to this channel, you'll be notified when the new videos are online. And with that, I'll take my dessert from the conference dinner, which I think is a swig of WD-40. Cheers.